Hi, hi, I'm from SQRT, and today I will talk about the progress and some research on developing the scalable benchmarking protocol for mid-circuit measurements. And I won't go through the technical parts. I will just be presenting some core concepts of those of our results. So don't be worried. So so, so the contents I will give some motivation for the benchmarking framework and some initial and standard methods developed before, and I will go through my research after that. So for the motivation part, so in these days, many big tech companies such as Google or IBM are building a lot of large content processors, and we have to know if those large processors are working right or not. So in that kind of domain, we need to develop benchmarking framework so that we can verify if our content processors are working right or not. So at the beginning, there was two ways. So first way is tomographic way. So it's kind of simple. We just measure all the components of the density matrix for the for some quantum process or maybe for quantum states, and rebuild those density matrix. So it's kind of exponentially costly with respect to the number of qubits, and it's quite sensitive to the state preparation and measurement errors. So after those inefficient or maybe not accurate way, we have built randomized benchmarking. So this is so we measure the average fidelity of some gate sets. So we don't have to measure all the components of the density matrix, so that this way is a lot scalable than the quantum process tomography, and also it is quite robust to the state preparation and measurement errors. And there are some historical records for the development of this randomized benchmarking. So I will just review how this framework is established and evolved. So at first, we just implemented some random unitaries and measured some survival probability, and we observed some exponential decay with respect to the number of quantum gates. So from this first work, we kind of, the researchers kind of know that maybe you can just implement random unitary operators and extract some accuracy of the gates more efficiently than the process tomography. But after that, we kind of restricted that random unitary gate sets to be Clifford and made some theoretical, or oh no, for some more protocol-wise established way, so that the the randomized benchmarking framework was kind of established and evolved more formally and experimentally showed through the trapped ion qubits. And after that, they more set up more theoretical assets about the scalability and for some errors like gate dependent or independent errors, and also for the time correlation errors using perturbation theory. So after that, they more completely proved those kind of scalability and error parts. Therefore, the standard randomized benchmarking started from like 2005, be completely proved and established at 2012. So this is how standard randomized benchmarking started and evolved through like 7 years. So let me just introduce how does this protocol works. It's quite simple. So the step one is you choose the M Clifford gates at uniformly random, and choose the final gate so that the total sequence is equal to the identity gate. And second, we just measure the probability for that circuit, and then we we obtain the average result for the result from step 2 and fit the result to the average sequence fidelity to the below model and extract the average fidelity of the gate sets from that fitted result. So it's very simple way and quite scalable. So that was the standard randomized benchmarking, and after that there were some initial variants of the RB. So first one is interleaved randomized benchmarking. So this is the motivation for this variant is, so one wants to measure the individual gate errors other than the average errors. So from the first standard randomized benchmarking, we only can extract the average fidelity for the whole gate set, but in the interleaved randomized benchmarking, we can now extract the error rate for only the gate of interest. So this was the first initial variance, and the second one is simultaneous randomized benchmarking. So for the motivation for this variant is also simple. We just want to know the crosstalk between the qubits, and how we do is just implement the RB simultaneously and compare the results. So we can see the write down plot so that if there were crosstalk between the two adjacent qubits, the exponential decay will be faster than the individual RB result. So this is quite simple and easy initial variant, and our let's move on. And nowadays we are also making a randomized benchmarking framework to benchmark the mid-circuit measurements. So let me just introduce what are the mid-circuit measurements are. So typically we only do the measurement at the end of the circuit. So that's called just terminal measurement, but we can also do the measurement inside during the quantum circuit. So that's just simply the mid-circuit measurement. And for that kind of measurements, there were two initial ways developed from other research group. So first one is kind of called a randomized benchmarking suit for mid-circuit measurement, and second one is Pauli noise learning for mid-circuit measurement. So first one is quite simple. In this method, they are using the simultaneous randomized benchmarking, which I introduced earlier, and they are probing the error signature of the mid-circuit measurements written in the left side of the table. So there are some error signature for the mid-circuit measurements, and they are probing those kind of error signature using the standard and simultaneous randomized benchmarking. So this was the quite first attempt to benchmark the mid-circuit measurements. But there's some restrictions that it's not scalable. They have to use the ancilla qubit to probe the mid-circuit measurements error rate happening in the control qubit, so it's quite not scalable. So next method is called Pauli noise learning for the mid-circuit measurements. So in this method, they use cycle benchmarking, and the cycle benchmarking is one of the type of the randomized benchmarking, but they are benchmarking the cycle of interest, which can be composed of any universal gates, such as non-Clifford gates as well. So this type of cycle benchmarking is quite scalable, but it only characterizes the cycle of interest. That means this method is not holistic benchmarking, and therefore the Pauli noise learning for mid-circuit measurement, this method is also quite scalable, but it's not a holistic way to benchmark the mid-circuit measurement. So the motivation for our research is those two previous methods are either not holistic or not scalable. So we wanted to make holistic and also scalable method for benchmarking the mid-circuit measurements. And how? We'll see the following slides. So I have to explain the binary randomized benchmarking first, because this is the underlying benchmarking framework for our research. So the circuit scheme is quite simple. At first, we have to prepare the some simple state that is stabilized by the random Pauli, and we have to implement the random circuits, and then we measure the Pauli eigenvalues at the end. So this technique is called Pauli tracking techniques, but we use the stabilizer theorem and randomized benchmarking framework together. So we prepare the random Paulis first, and we send to the random circuit to be evolved to the random Paulis, and then we just measure the evolved random Pauli at the end and extract the average error rate using the randomized benchmarking framework. So this circuit is scalable to the Clifford gate, but only the bad thing is that we cannot use the non-Clifford gate in the random circuit part, which was quite bad compared to the cycle benchmarking. But still, we are not using the universal gate, but this method is scalable and also holisticer and also highly accurate method up to date. So we adopted this framework for our research. So in our research, there are some error signatures we considered for the mid-circuit measurements. So there are measurement-induced control error and local measurement error, and also residual GG interaction, which typically occurred in superconducting circuits. So you don't have to go through all kind of errors. I'll just talk later. So first scheme is effectively measurement induced control error free scheme. So which simply means that we can effectively ignore those red colored errors in the first scheme, but we can add those control error into the scheme 2. So for the first scheme 1, we can isolate the mid-circuit measurements from rotation gates, which kind of effectively excludes the measurement induced control errors. And in the scheme 2, we're just effectively adding those kind of errors. So we can separately measure the error rates with or without the measurement induced control errors within the binary randomized benchmarking and also interleaved randomized benchmarking. So this result is from the noisy simulation result. So we have to verify if our protocol really works or not. So we plot it with the input noisy values and error rates in the y-axis. So from the 3 plots, we can see that for the error signatures I introduced in here are all well matched with the experiment results. So we verified our validity of our protocol using this kind of noisy simulation, and we also checked or implemented our protocol in the real experimental hardware. So we used IBM's QPUs, and we also checked those 2 schemes here, and we could kind of extract those average error rates from the mid-circuit measurements like that. So those were the first progress and some recent results of our research, but there were some pros and cons in our approach. So the pros is since we used the interleaved randomized benchmarking framework, we could easily extract the fidelity of mid-circuit measurements, but the interleaved randomized benchmarking method has some high uncertainty in measuring the obtained fidelity. So we wanted to make better. So how is just simply not using the interleaved randomized benchmarking and put the mid-circuit measurement into the gate set of interest. And to do that, there are some problems such as projective mid-circuit measurements collapsing entanglements or exponential overhead, or also the mid-circuit measurements error channel is not a stochastic channel that it is quite hard to just simply incorporate the mid-circuit measurement into the gate set. So for those kind of potential problems, we have found some ways to avoid those problems. So those are some answers to the mentioned problems. So first one is that we have to use the mid-circuit measurements as a random multi-body way. So it is quite not easy to explain why we have to do that, but you can ask me later if you're interested. So in by using the random multibody mid-circuit measurements, we can ensure that even though we are using the mid-circuit measurements in the random quantum circuit, we can still make the volumeless scaling of the random circuits that we can, at the end, in theoretical way, we can model the total circuits into some kind of depolarizing channel or polycircuit channels. And also, we are using the stabilizer theorem and the binary randomized benchmarking so that we can avoid the exponential overhead problem. And finally, by using the randomized compounding technique, we can model the non-trivial error channels of the mid-circuit measurement into simple stochastic channels. So those kind of problems is our work in progress. And yeah, so this is the end of my talk. And those are the slides and references. So if you have questions, you can ask me now.